I mean, at least like for this class, does this format seem to be working okay for you?
Yeah, I just gotta keep up with the lectures. Um,
Yeah. Okay. That's good. Has that been working for you?
yeah. Um, it's kind of crazy when other classes pop up things like last minute. So I feel like this is the class that I'm like, okay, I got everything on schedule, and then everything else kind of just pops up randomly
Oh,
with
okay.
other classes. So,
So, but this
but
class
yeah,
to be at
but this,
least
yeah, this,
regularly. Yeah.
mhm.
So with other ones, it's like, okay, we're going to do this at this time or something, and you don't anticipate it or something.
um, well, so like a lot of different classes, they're like, well, I'll just upload the lecture by this time. And then I think there's a little bit of trouble since we're just getting used to Canvas for the first time. So they'll like say, okay, I put it up there. And we're like, we can't see it. I
Okay.
don't know. I don't know where you put it, but I can't see it and I can't do anything about it. And some of the pages have changed pretty quickly, like home pages, more quizzes and stuff to make sure that we're keeping on top of stuff has also popped up. But um, I don't know. I feel like I get like 15 to 20 emails a day of just like things moving around in Canvas
Oh
from other
man.
classes. And
Okay.
it's like, oh, this professor put this on Canvas, but it's not published yet. So then when it gets published, we get another notification on top of it. And
Yeah, I know.
I don't know.
I know that that's happening because I was messing with like test student stuff and just trying to see things from a student perspective, and even like, I mean, I know that you guys are being inundated with communication. So, and I know that every time I would schedule a Zoom meeting in Canvas, that it would send you a notification. So I was like, I'm not going to even do that because it's just going to fill up your inbox even more and it's going to get buried. So, um, and I also knew that every time I did something in Canvas, like uploaded a lecture or something, that it sends you some kind of notification. So I think that minimizing that is probably prudent at this point. So that's why I made the YouTube uh, that's why I made the YouTube channel. That's why I just said, look, I'm not going to send you any more notifications. Just go to this website at the times of class, and for sure I'll be in there. So hopefully that's at least streamlined some things. I knew that that was probably happening across the board. So
Yeah, it was definitely interesting the first couple days because things would move all around Canvas, and then if anything was changed last minute, then you went through like 4 more updates of what they went through the same process again. So, but no, it's
yeah,
been really nice to have it on YouTube and just be able to go over there and
that's good.
work through.
I mean, I'm glad that worked out for you because I also know that Anthem, Ensemble Anthem was being kind of glitchy at times. So it was, and some students that don't necessarily have really good internet access were having major issues with that. Um, and even some that did have good internet access were still having problems. So it just seemed like going to YouTube was a natural thing to do. Sorry, I'm weirdly putting myself in here again because here, let me fix this. There we go. Okay. I always get this in here because then I can easily write in here. Okay. So anyways, yeah, I'm glad that at least as far as this class is going, it seems to be working all right. So the lectures make sense for the most part.
Yeah, I've been going through the notes and then trying to go through the homework too, right behind it.
Mm-hmm.
But
Okay.
yeah, it seems to be pretty good. Yeah, the only thing I got stuck on was just the chi-squared distributions. And I
Okay.
was like, okay, I just got lost on this one. But
Yeah.
um,
So was there a part in particular that seemed tricky, like, you know, that wasn't making as much sense?
well, so I'm just trying to follow what's going on with the distribution. It seems like there's like, is there like only one distribution that is the chi-squared, kind of like how we have the standard normal distribution, or like,
Well, so like the normal distribution, there's infinitely many, right?
okay,
There's infinitely
Yeah.
normal distributions. Like, you could have any mean you want and any variance that you want. The shape of the distribution is always going to look similar, right?
Mm-hmm.
But there are infinitely many normal distributions. And to fix that problem, that's why we convert things to z-scores and use the standard normal. So
Okay.
it takes all these infinitely many and hones in on one distribution is kind of like the standard one. Does that make sense?
Okay.
Chi-square, unfortunately, the chi-square there are infinitely many distributions, one corresponding to each number of degrees of freedom. Okay, and there isn't some way to like normalize all those and get down to one. So you just have to deal with the fact that there are infinitely many chi-square distributions.
Okay.
But
With the
there are also infinitely many exponential distributions, right?
okay.
One
Mm-hmm.
corresponding to the parameter, each corresponding to the parameter lambda. And there were infinitely many Poisson distributions, right? Each one had its own lambda, but the formula looked similar for every one of those, but it was different for every lambda. And there were infinitely many gamma distributions, yeah? So the normal is the one case where we can like, take all of them and go whoop and put them all in one place and do our computation there and then translate it back later on if we have to.
Okay.
Does that kind of make sense?
Yeah. So what are we doing with the degrees of freedom? I guess where does that come from, or what is it doing?
So, I mean, there was this. So let me kind of pull this up. That's not what I want. What do I want here? And neither is that. Okay, just a second. You cannot minimize. What? What do you mean I can't minimize? Tell me I can't minimize. Here, I'll go like this. Let me pull this up so we can look at it. Okay. Read that.
Mm-hmm.
Okay, so there's where the chi-squared distribution was first introduced, and it came from the gamma distribution. And remember, with the gamma distribution, what we're doing is we have a Poisson process, and with parameter lambda. That is, lambda is the number of observations we expect to see in our interval of time or whatever, right?
Mm-hmm.
And what we're doing with the gamma is we're waiting for the alpha occurrence. Alpha is a parameter that tells us, that we're waiting, like alpha could be 5. So we're waiting for the 5th occurrence and we're just tracking the amount of time. That's what the gamma distribution is.
Okay.
And beta is just 1 over lambda, right? So beta itself is 1 over lambda. And by the way, 1 over lambda is the amount of time you expect to have. So beta is literally the amount of time you expect to have to wait for one observation, right?
Mm-hmm.
That's why, incidentally, like if I expect to see lambda equal to 2 observations in 1 hour, how long do I expect to have to wait for one observation?
2 in 1 hour. So like 1.5 an hour.
Half an hour, right?
Mm-hmm.
Expect to see 2 in an hour, then you expect to have to wait half an hour to see 1. Does that make sense?
Mm-hmm.
What if I expected to see 6 observations in an hour?
then you're going to see
Like, you have to
one
wait.
every 10 minutes.
Yeah, right. 1/6 of an hour. So do you see that, like, whatever lambda is, basically 1 over lambda is how long you expect to have to wait.
Okay.
Does that make sense? For
Yep.
each observation. But beta in here, so here I'm kind of going like this, beta is equal to 1 over lambda. So is it any surprise that if I'm waiting for alpha total observations, it's going to take alpha times the amount of time for one observation. One observation is beta, and if I'm waiting for alpha of them, then I expect to have to wait alpha times beta amount of time to observe alpha observations. I know we're saying a lot of Greek letters here, but hopefully that kind of makes sense. Does that kind of make sense?
Yeah, that makes sense.
So if you understand the gamma, then the chi-squared distribution is basically just a special case of it.
Okay.
The chi-squared distribution is just the gamma distribution, where what you're trying to do is get rid of the dependence on two parameters. Okay, like,
Okay.
and all you're doing is you're saying, well, what was beta before? Beta was the amount of time we expected to have to wait, right?
Mm-hmm.
So beta was equal to 1 over lambda. So lambda here would be like 1/2, which is kind of strange, but beta is like 2 is the amount of time we expect to have to wait to observe one thing, and then we're waiting for the r over tooth. Right, because alpha was, we're waiting for the alphth observation, yeah. So
Mm-hmm.
waiting for the r over tooth observation, and the reason you do that is because what's the expected value going to be? Alpha beta,
Yeah.
which is r. Does that make sense? In this case,
Okay.
So now you only have one parameter instead of two parameters. You don't have alpha and beta anymore. You just have one parameter, r. You might say, why would I care about such a specific thing? You know, this,
Mm-hmm.
because chi-square is just a very specific case of the gamma distribution. Well, it turns out that comes at the end of the here's this, right? The mean is r, because that's what
Mm-hmm.
alpha times beta is, yes, for instance. And then we just use all the other information to get that. And the notation we use is chi-squared of r. The reason we care about this really is at the end of the presentation here. Turns out that if you have a normal random variable, then if you square the the standard normal, you end up with a chi-squared distribution. So the square of a normal random variable is chi-squared. And I'm just telling you that I'm not explaining why that happens to be the case right now. But it turns out this is the motivation for why we care about the chi-squared distribution at all.
Okay.
And that's just with 1 degree of freedom. So r is equal to 1.
Okay.
So back here, did it make sense what this was? This
A little bit.
huh?
A little bit.
So let me see. I'll draw a picture of this, okay?
Okay.
So what this is saying, and I think I may have, there's a chance I drew a picture in the lecture, but I don't quite remember if I did or didn't. Okay, but here, let me share some stuff here. Okay. So the probability, oops, wrong thing. So chi-squared sub p of r satisfies the following. It says it satisfies that the probability that X is bigger than or equal to this thing, is equal to P. Okay? Where X is simply distributed as chi-squared with r degrees of freedom. Okay? So here's the picture. Chi-squared looks like this. Okay?
All right.
What a chi-squared distribution looks like. And essentially what you're doing is this number chi-squared sub p of r. The probability of being beyond that is the area beyond it. Does that make sense?
Okay.
And what we're saying is that right there, what's that area going to be?
One minus the area on the opposite side of it.
Well, yeah,
Or-
but here we've said the probability that we're beyond that is,
Oh, it's P.
yeah, it's just P. It's the percentage in the tail beyond this thing. So this thing has the property that there's P% in the tail beyond it.
Okay.
So like this example, okay, so we did a couple of examples. So we wanted to find chi-squared of 0.025 with 17 degrees of freedom.
Mm-hmm.
Okay, so let's do that. So we want to know what chi-squared, oh man, what in the world did I just write? Okay, we want to find chi-squared with 0.025 with 17 degrees of freedom. What is it? Okay, well, we know, look, just draw the picture. Okay, so here's the chi-squared distribution. This thing that we're looking for, 0.025, 17. It's going to have the property that how much area is going to be right here? How much area do we want right here?
0.025.
Yeah. It has the property
Okay.
that there's 2.5% of the probability is over there. But that means, what does that mean about the percentage of stuff that's, what does that mean about the percentage of stuff that's, sorry, I'm being obsessive here. That didn't look like a 0 to me. Okay. What does that mean about the percentage of stuff to the left of this?
It's 1 minus that
Yeah.
probability.
So 0.975 basically, right?
Okay.
So that means, and incidentally, the X we're dealing with here is chi-squared with 17 degrees of freedom. Okay.
Okay.
So we're trying to determine what this is. We're saying, what is this thing? Okay. And it's basically, it's a percentile. Yes.
Okay.
This number is at the 97.5 percentile, 97.5th percentile. That's where this thing is.
Oh, okay.
So, I mean, basically you could say chi-squared sub p of r is the 1 minus pth percentile. Well, 100 times 1 minus pth percentile. Okay, so that number is at the 100 times 1 minus pth percentile. Okay.
Oh, okay.
Now we can use like Excel to find this thing. Okay, so can we do that? Or like there's
Sure.
tables. Do you have your book with you?
I do.
So if you flip in your book to page, see, where is this thing? Table. Didn't you say something in your email about some of these tables?
Yeah, I think it's table 4 in Appendix B.
Yeah.
We don't have
So,
page numbers on these tables, though.
So you see that there's the second to last column on
Mhm.
the table. It says chi-squared of 0.025 r. And then the
Okay.
degrees of freedom are given down the left-hand side. You see that?
Mhm.
And so chi-squared of 0.025 r, it's just guaranteeing that you have 2.5% to the right of whatever that number is. And what do you see it gives you if you go to the 17th degree of freedom row?
30.19.
Yeah, that's right. And so there's going to be 2.5% to the right of that. And you see right above at the top of the column, it says 0.975. That's just
Mhm.
giving you, well, that would be the probability of being less than or equal to that thing. Yeah.
Okay.
They say 0.975 is the probability of being less than or equal to that. 0.025 is the probability of being greater than or equal to that thing. So this guy right here, oops, sorry. This guy right here ends up being equal to, what did you say it was again?
30.19.
Okay, 30.19, exactly right. So, but we could have also gotten that from Excel. How? Well, let's go over. So we got it from the book or from the table, right?
Mhm.
What table was this? Table,
4.
yeah, table 4 in the back of the book.
Mhm.
But we could have also gotten it in Excel, and here's how. Here, let's go to Excel. Let's go to Excel. Okay, so, all right. So what do we want to do here? Equals, what do you think I would want to start typing, Christy?
Chi-squared, or
Yeah,
at least chi.
chi-squared. And here, because this comes up so often, do you see this? There's like, there's a regular chi-square, and then there's like a right tail one as well, because it turns out that when you use chi-square later on, like the right tail stuff is going to end up being most important. Like how much percentage is beyond it, not before it. Whereas
Oh, okay.
probability computation has been before the thing, like, all the probability up to this. For chi-squared, a lot of times you just want the right tail, so you have to be kind of flexible with that. So this says returns the right-tailed probability of the chi-squared distribution. That sounds like exactly what we want, doesn't it? But we don't want the probability because we already know what that is. We want the
Okay.
number beyond which gives us that probability. So which of these functions do you think we should use?
The inverse right tail.
Yeah, the inverse right tail will do that because that's like saying, I already know the probability, excuse me. Now I actually want to know the X value that corresponds to. Does that make sense?
Okay.
So if I use that, I use the right tail one, what's the probability beyond? So this is the probability in the right tail. So what would I type in here?
0.025.
Yeah. And the degrees of freedom,
17.
yeah. And that gives us exactly the same thing that we got from the table, right? But it's
Mhm.
actually even more accurate. Okay.
Okay.
Is that helpful?
Yeah. I think I was looking at it differently when I went through the percentiles for some reason. Um, I don't know why. I think I just like moved my decimal points all over the place and was like, I don't even know what I'm looking at. But that makes more sense.
Okay.
Um, the one question I was stuck on was number 17. Um, I guess getting started with this is a little bit harder than I thought. Like when it tells you like, hey, here's the percentile and here's the degrees of freedom, you can like make it through the table necessarily and find it, but um, I don't know, I was a little stuck on that one.
What are you talking about? 3.2?
3.2, number 17. Yeah.
Okay, so what's the probability? Okay, so oh man, let me do this. Okay. What is the probability? So how many degrees of freedom did it say it was? X was what?
There's 4 degrees of freedom.
Okay, so I'm going to use a different letter since I'm on the same page as this other stuff, but
Okay.
so if y was distributed as chi-squared with 4 degrees of freedom, okay?
Mm-hmm.
They're saying what is the probability? Okay. Okay. Find the probability that at most 3 of the 15 observations exceed 7.79. So I'm just doing one observation, but right now. So what's the probability that y exceeds this thing? Well, there's a couple of ways we could do that. So this is just one observation, right? There are
Mm-hmm.
a total of 15, but we're just doing one right now. If
Okay.
we can handle one, Christy, we're in trouble, right? I mean, because they're if they're asking us about 15, I'd better be able to handle one. I need to be able to figure out, okay, what's the probability that this observation is bigger than 7.79? Okay.
Okay.
So if you go to that table again, which row am I in?
R equals 4.
Yeah. Do you see a 7.79 somewhere?
Mm-hmm.
There it is. Under which column?
Chi-squared of the 10th percentile.
Yeah, chi-squared sub 0.10, which is at the 90th percentile. Yeah.
Oh, right. Sorry. Yeah.
Yeah, because remember the sub-index there means that there's 10% beyond it. Yeah.
Okay.
So what is this probability? What percentage of data is to the right of it?
To the right is 0.1.
Yep, 0.10. Exactly right.
Okay.
Okay. And you could have done that in Excel, right?
Okay.
You could have said, hey, let's go in here and do this. I could have said, what is the probability? Okay, so the probability that y is greater than 7.79 or 779, where what's y? Y is distributed as chi-squared. I'll just do chi with what?
4 degrees of freedom.
Yeah, actually, I'll just go xi for chi with 4 degrees of freedom. Okay, so what is this? This is going to be equal to chi Okay, so
Uh,
it gives me the option for how much probability, uh, for a right tail probability, yes? And
mhm,
exactly what I want here. I want to be beyond this. Does that make sense?
mhm.
So I would select the right tail one. I could have used the cumulative by distribution function by doing 1 minus the other one, right? But what's my x in this case?
7.779.
Yeah, degrees of freedom,
Or
right? And
okay.
we got the same thing, didn't we?
Mhm.
As we did from the table, 0.10, okay? So let's go back and now let's kind of think this thing through. Okay, so there's that. But I have 15 of these, right?
Mhm.
The probability, and what was it? It was the probability that at least what?
At most 3 exceed 7.779.
Yeah. So you know, uh, let's let W equal to the number among, hang on, so among 15 observations of Y. Okay, so you just kind of let Y go over and over and over again. It's going to be a bunch of independent trials. Yes. Okay.
Okay.
Right. So the number of observations of Y, 15 observations of Y that do what?
Um, they exceed 7.779.
Yeah, that exceeds 7.779. So like P, which is equal to the probability of success, is going to be this probability right here. Probability that an observation exceeds this thing. Okay. Which what is,
Okay. 0.10.
okay. And so if you think about it that way, what's going on here? I have 15 trials.
Mhm.
They're independent trials, and the probability of success, right, is P equal to 0.10. So what's the distribution of W? Fifteen trials.
Uh,
I have a proportion of success. Remember?
um, let's say geometric, but binomial.
Yeah, and that's with N equal to 15.
Yeah, 15.1.
And what's my proportion of success? And so what is the question asking?
The question asks, find the probability that at most 3 of the 15 observations exceed 7.779.
Okay, so translate, Christy. Translate that into stuff with W.
Okay, so the probability that W is less than or equal to 3.
Yeah. And that is what you need to find. Okay.
Okay.
And I think that I mean, you can even use, I think there's tables in here. There are, like table two would help you do it, or you could use Excel, right? So we have n
Okay.
equal to 15. Does this table go up to 15? I think it does, yeah. See that?
Yep.
And I think, what in the world is this table telling us? Is this the cumulative distribution function?
Um,
Yeah, it's the cumulative.
okay.
So for instance, if you went down, if you go to n equal to 15, and then you go down the column corresponding to 0.10, do you see that?
Mm-hmm.
Then you would want the entry corresponding to x equal to 3. You see?
Mm-hmm. Oh, okay.
So the other way to do it, though, would just be with Excel, right?
Yeah.
Right? So you'd go like, you would go equals binomial distribution. How many successes do I want here?
3,
Trials,
15.1.
portion of success. And do you want to add all of them together up to that point?
Yeah.
Yeah. And that's exactly the same as that table value, right?
Mm-hmm.
So,
Oh, okay.
so you kind of,
Yeah.
you set the problem up using the chi-square, but you set the problem up using the chi-square, but then you like go and use the binomial distribution to answer the question. Does that make sense?
Mm-hmm.
So yeah.
I think I was trying to make the chi-squared distribution do something else for me, and I was like, I have no idea. I was trying to interpolate in the tables, and I was like, oh my goodness, I
No, yeah, the chi-square
can't find
distribution
this.
is simply telling you the proportion of success. That's it. Yeah.
Oh, okay.
And that problem should have an answer in the back of the book, I'm pretty sure.
I can check it real quick. Yep. We got exactly what we got in Excel and also in the table. So
Yeah, there you go.
awesome. Well,
More
thank
sense,
you.
hopefully.
Yeah, that makes more sense.
Cool. All right. Well, anything else, or is that pretty much wrap it up for you?
I think that makes a lot more sense now. So I just got to keep working through everything else. Thank you so
Okay.
much.
Yeah, no problem. All right. Well, don't hesitate to reach out if something isn't making sense. I'm just gonna keep on posting the lectures, and you can just keep asking questions. That's what this time is for. Also, I'm all on Monday, Tuesday, Thursday, and Friday. I'm in this same Zoom room from 8:30 to 10. People just kind of pop in. So yeah, but
Okay.
this time right here is reserved for only this class. So yeah.
Great. Well, thank you so much. I really appreciate it.
Yeah, no problem. All right. Have a nice weekend.
Thank you, you too.
Yep. Bye-bye.
Bye.